Hello everyone and welcome back to my channel. I'm going to recreate a very old video of mine where there was very poor audio quality. And this is going to be all about how to predict remaining useful life of turbo engines. If you do not know what is fault prognosis and everything, I already have a video about this. I'll put it in the I button and in the description so you can go and check it out. It's a purely introductory video about what is fault prognosis with very simple examples. But in this video, we are going to focus on how to predict the remaining useful life for turbo engine. It was basically a challenge given by NASA back in the day. If you want to download the data for this challenge, I would like you to go here. I'll put the link in the description. NASA turbofan jet engine dataset, and you can directly download from here. Probably you have to sign in into Kaggle. Okay, this was the previous video which I made on this, but it has very poor audio quality. So I'm recreating this video again. So let's understand what we have to do. So first of all, we have an engine, a turbo engine like this. And what happens is whenever the engine runs for various cycles, in here, one cycle means it goes from destination A to destination B. And here you see as the number of cycles increases, the health of the engine keeps on decreasing, which is very normal. Like they have all finite amount of life. But what we can do, like this is a very nonlinear curve and it's very difficult to predict for different type of engine that how it will follow. Sometimes it will immediately drop. For example, in some cases it may happen like it will drop something like this. For something it just goes on and it takes a lot of time to degrade. Then what happens is if we, let's say we fix, okay, this is the amount of time after which we are going to do fixed maintenance, then it's not very ideal. Then what may happen is, so for example, for this engine, which could have ran for, let's say 20 more cycles, you are losing it and you are doing the plant maintenance before. So in this case, what we do, predictive maintenance, that we predict when the model, when the component is gonna fail, and we plan our maintenance according to that. It's definitely not an easy task and it's very difficult, but there is a lot of money involved in it if you could do it accurately. So a lot of companies are investing heavily on this particular domain. All right, so that is the goal, that for what we have to do is for each time when our engine is running, for example, this particular time interval, we need to predict for how many more cycles this engine can run or at what cycle it will fail. For example, here I gave an example. So let's say this is my curve, the health of the engine curve. And let's say my engine failed at 500th cycle. I wrote here, this is where the engine failed. And this 500th cycle is what I call end of life. So my goal is for any particular number of cycle, let's say I'm at the 43rd cycle, let's say. I want to predict for how many more number of cycles my engine could run. And I call it remaining useful life. All these terminologies are well explained in the video I referred at the first. Here, my remaining useful life will be nothing but 500 minus 43. That will be my remaining useful life. So for example, let's say I want to see at my remaining useful life at the 100th cycle. Then it will be 400 because after 400 cycles, my engine failed. So let's more formalize it that what we want to predict. We definitely want to predict this remaining useful life and how we can do it. The remaining useful life may look very simple, that okay, for one engine for which we already know that when it put in this engine failed, for this case it was 500. So what we can do is we can just subtract that value from all the cycle. For example, at 0th cycle my remaining useful life was 500. At 100th cycle my remaining useful life was 400, and at 500th cycle my remaining useful life was 0. Very logical. And what I could do is I could just, for number of cycles, I could just subtract the value of my end of life. This looks very simple, a very linear curve, but it's very difficult to predict. But what happens in case of machine learning is, suppose I think that I want to predict remaining useful life, but it's not a very good target for a machine learning model, because for some engine it could have like range from up to 500. For some cases it may go up to 1000, and for some cases it may go up to 5000. The range is extremely variable. So what I would like to predict instead is something called life ratio. It is very simple. Instead of subtracting from the current time the end of life, what we get from RUL, what I do is I divide the current life cycle, current cycle time divided by the end of life. So I get a ratio. So when it's 0, that means my model is just starting. When it is 1, that means I am at the end of life. And from this you can easily get the remaining useful life if you want. But this is going to be our target that we would like to predict, because in this case the value ranges only from 0 to 1, and it's very easy for machine learning model to regress over. But now let's understand a little bit what is the health of the engine, what we are talking about. So let's say this is our engine. Then how we measure this health is based on the sensor, because the sensors are our window to look into the health of the engine. So we have various sensors established in this engine. There are temperature sensors, pressure sensor, speed sensor. And how does it look like? They in this data set. Yeah, you see in this data set they have given all these values in txt format, but I want to convert the txt into a CSV file, in pandas CSV file, so that I can operate on it easily. And this is how it looks like for one training data. So the first column represents unit number, where unit number represents one engine. That means unit number 1 represents the first engine. Unit number 2 represents the second engine. And for the first engine, this data is collected until it failed in the training set. So time in cycles means for the first engine, this is the first cycle, and this is the reading of sensor during the first cycle. Then for the second cycle, and it goes until the first engine failed. Then after that, it starts for the second engine, first cycle, then second engine, second cycle, and so on and so forth. So in the first training data, there are 100 different engines who have different who ran for different number of cycles. Now I'll jump to Jupyter Notebook. First, we'll import some libraries such as pandas, NumPy, matplotlib. Seaborn is not even needed, but yeah, let it be. So when you download the CMaps data from Kaggle, it will look something like this. There is the paper in PDF format, and there are like txt. During the training, we'll use this train FD001, train FD002, 003, and 004. These are going to be our training data, and these are going to be our test data. So first of all, we have to read them. And to read them, I'm using pandas read CSV method, and I'm passing the location of my train FD001. So just to get a approximate idea of what my sensor, these are all the sensor values. Okay, the first one is, I think, the ID of the engine. The second one is number of cycle, at what number of cycle these readings are calculated. And the rest of all are just the sensor values. And directly you can see that this 25, 26 and 27 are useless. They just contain nano values. So we can just ignore them right away. And also there are some features. For example, you see the standard deviation is 0 for this particular feature. That means it doesn't vary at all. It stays, the mean value is 100, the max value is 100, and the mean value, that means it doesn't change at all. So this kind of feature do not contribute anything towards prediction of the RUL. So we can directly ignore features like 4, 5, where standard deviation is absolutely 0. But we'll see them in detail when we plot them. So first of all, I'm just deleting the 26, 27 because they are just garbage values. Now I'm renaming all my columns. After renaming my column, I see they look much better. All right, the first one is the unit number, then the time in cycle. And now I'm going to plot them. So you see, this is for the unit number, then time in cycle, setting 1, setting 2. And for this example, this TRA, it doesn't change at all. So this kind of feature doesn't have any predictive power. So we can neglect them. So this also T2 also. There are few features. Yeah. So is this one. So that's what I did. And I deleted the column which do not contain any information in the prediction. Basically who do not change. Now what I want to do is I want to create a new column. I'll call it, let's say, live ratio, that I explained what is live ratio in the previous section, that the live ratio at the starting is 0, but it goes to 1. For example, let me just so what I'm doing is I'm only taking the rows where unit number is equal to 1. That means just for the first engine. And here you see that there are total 192 rows. That means it went for 192 cycles. At first, my live ratio is 0, but it goes up to 1 when my engine failed, basically. All right, you can do it for, like, let's say 2 for the second engine, and it changed. It went for 287 cycles. All right. And now what I want to do is I want to see what features in my dataset contribute towards are basically related to my output prediction, which is in this case the live ratio. For that, I plot a correlation plot. So what I'm only concerned about this row. For example, live ratio. Live ratio is very weakly correlated with the engine serial number, because which is very normal also, like given engine number, it shouldn't have any correlation because we can give randomly, like depends which engine you took. Time in cycle is very highly correlated because basically we use time in cycle to calculate live ratio as very high correlation. Setting 1 and setting 2 are very weakly correlated. However, T21, T30, they have good correlation. This one is weak correlation. So negative correlation doesn't mean weak correlation. It means just they are like when the live ratio increases, P30 decreases, something like that. So what we do not want is 0 correlation, close to 0, like this. This is bad, but this is good. So yeah, you see many of the features have good correlation except for setting 1 and setting 2. We can probably neglect setting 1 and setting 2 when we model our machine learning model. So now I use sklearn to import random forest and train test split and mean squared error. So when I obtained feature for the training, I dropped setting 1, setting 2 and live ratio because that is my target. And this y is my target, which is the live ratio. So I pass it through my train test split. I put 20% as my test size, and my random forest model is already trained. I used 100 decision tree inside it. And now you see my prediction y pred is this is the prediction mean squared error, which is 0.0036 on my test data. So here you see for, let's say, fifth engine, the prediction very closely follows the true live ratio. Let's do for this one as well. But let's see on the test data, because this is important. We need to basically do it on the test data itself. And then I did the same operations that I did for the training. During the training, I dropped 25 and 26 column. I rename all the columns. I removed the uncorrelated columns, and then I created a new called live ratio. I created a new column called live ratio by just taking the ratio between current time instant and the end of life. And you see, this is the prediction on my test data. It's not very as accurate as what it was for the training, but for the test also is pretty good. I think we can do the first one. Yeah, For the first one, it's not very good. You see at the starting it's pretty close, but at towards the later part it diverges. Yeah, for some it's good, for some it's bad. So let's accumulate all the testing data we have. I just run a for loop for all the testing data. So yeah, on the entire test data, when I do my mean squared error is 0095, which is pretty high. Here I think it was on the training data is 0.0036. Yeah, so it's a very clear case of overfitting. But what we did till now is we just trained on this one file. Right now we just train on this train fd001. But what we should have done is we should have trained on all 4 files. So that's what I did in the next step. So it's very easy. What I did is the same process, but instead I created a larger training data processed. I looped through 1 to 5 and basically, so this is how my train data processed looks like. And here, just don't get confused. Here, RUL is live ratio, by the way. Then I created my XY. I created my random forest. It takes a while, by the way. It takes like 4 to 5 minutes depending upon your CPU. So I'm just gonna load the one I trained before. And you see here on the training data, after training for on all the 4 training sets, I get 0.0040. And during the test, I did the same. Yeah, on the test, I get 0049. Definitely it reduced from 0.9 something to 0.49. It's a pretty good result. So yeah. So now what I'm doing is I'm taking, let's say this one, test fd002, and I want to visualize the results. So you see, this is for the first engine, second engine, third engine, fourth engine. The yellow one is the prediction and the blue one is the true. And you see, more or less it follows. And the more it follows, the better is the prediction. So yeah. What I also did is you can go and follow. I already uploaded all this code into my GitHub. I also trained a neural network instead of random forest. But most of the things stays the same, but just this part, the dataset creation part changes a little bit because the PyTorch accepts a data loader, and it's better to use a data loader to not get out of memory error. This is my simple neural network model. In this simple neural network, I have like 3 layers, each having 256 neurons in them. I'm using leaky ReLU as my activation, and finally a linear layer at output is 1. And I trained this model, and what I want to show you is, see, the mean squared error did not decrease much compared to the random forest, because in random forest I think we got around 0.0049, and here I think we got 0.0053. Probably if I run it for long enough it may reduce, but I did not do that much. If you are interested, you can definitely go ahead and do that. So one thing to note here is the file path. You have to change it according to where the this txt file lives in your system. I also trained a CNN model, a 2D CNN, by taking a sliding window method. Till now, I was just taking this one row as input to my model. But after that, what I did is I took this like the whole window length of sensor data as input. I also trained a CNN and also an RNN. So this will be my input at once, then this will be my input, then this will be my input, this will be my input, so on and so forth. And for example, if suppose this is my input, then the live ratio for this particular instant will be my output of the model. That's what I did in this P4 RUL prediction CNN all data. But here I found the worst performance. It was performing the worst among all. The modifications were, I think, just here. So this is, there are 2 models here. One is RUL CNN 2D and RUL LSTM. You can try with both. The main difference was here, that where I did the sliding window based data creation. Then the rest were pretty similar. And you see the mean square error did not is 0.031. It did not decrease much. Even I ran it for 20 epochs at once, but it did not decrease much. That's why I thought the better idea is just to use the random forest. It's very fast to train and gives the best result in my opinion. So yeah, that was all about this video. If you have any doubt about any code or anything, do not hesitate to either create a pull request on GitHub or just comment it here in the video. I hope you enjoyed this video. Till next time, stay curious.